Section 6.1 is on page 298, talks about systems of linear equations, which are matrices. So linear equations, if you remember, that's when the power and the variables equal 1. And what's so special about linear equations is when you sketch the graph of a linear equation is represented by a straight line. So this is continuing when you did systems of equations 2 by 2 and 3 by 3. But there's more efficient way to do this using matrices. A matrix takes the following notation. These are the notations for a matrix. And what's a matrix? A matrix is defined as a rectangular array of numbers. It's really a list of vectors. So, magnitude of a vector, matrices is a list of vectors, just a list. And we have rows and columns in a vector. Nothing's working out right today. And here we go. Better. Okay. So, this right here is really equation 1. This is equation 2. And the list goes on. This is the first variable. Now, we normally call them x, y, z. Sometimes they call them x sub 1, x sub 2, x sub 3, and the list goes on. But they are nevertheless variables. Now, we're going to start with the first notation. You know what? Let me put that right here. This is x, this is y, and the list goes on. Now, the first type of matrix that we deal with is called an augmented matrix. And the way augmented matrix works is as follows. We take a system of equations and we take the first equation and copy it right there. And we take the second equation and copy it right there, but without the variables. And the equal we denote with that line. The new books of linear algebra are starting to exclude that n, but to us it's no big deal. We just want to get this out of the way. We'll worry about that when we get there. So, what an augmented matrix is, the best way I could kind of elaborate on what you know, is syntactic division compared to long division. Long division, you kept all of the variables. Syntactic division, you just wrote the coefficients. An augmented matrix is taking the coefficients and putting those in order. It has to match. So you have to put the x's lined up, the y's lined up, and the constants lined up. And then you could create an augmented matrix, and that's the first set of problems we're going to tackle. And on page 309, we start with the first set of problems. Simply take a system of equations and write it as an augmented matrix or an augmented matrix. Now, if you can't find this in your book, if you bought the book, the traditional book, not our PCC book, I already uploaded all of these sections and all the answers in Canvas. You could find them under files. So, we would use the matrix notation. For the equal, we will put a line, and we simply copy down the coefficients. For the x, a 3 and a 4. For the y, a 4 and a negative 2. And for the constants, a 7 and a 5. And that's pretty much it. That's the augmented matrix. And here we want a 3 by 3, so we leave a bit more space. And the x's, a 2, a 1, and a 1. The y's, a 3, a negative 5, and a 2. And the z, a negative 4, a 2, and a negative 3. And the constants, 0, 0, and negative 2. Oh, oops, I messed up. Look at that. Tricky. Tricky, tricky. This right here is a constant. I should move that to the right. So there's no z there. And that's a negative 2. Wow. Good thing I thought that. Interesting. Okay. Now to elaborate what they're going to do, it's a bit confusing, but to really make that a smooth transition, they're giving us a system of equations. I would like to take this system of equations out of the augmented form and write it as is. So if this is the x, that is x, and that is 2x. That's the y, and those are the constants. So this is minus 3y equal a negative 3, and this is minus 5y equal a negative 4. And I'm going to ask you a simple question. Remember, you did this in college algebra. You solve systems of equations. If I take those two, and if I want to get rid of x, how do I do that? So wouldn't you say multiply the top equation by a negative 2? Wouldn't that become negative 2x plus 6y equal a 6? And this will remain as is, untouched. And if I add those, what do I get? Right? So, guess what? Now, matrices are used to solve more systems and equations, like 5 by 5, 6 by 6, 7 by 7. Now, if I look at number 20, what they want, well, let me go back and recap. What did I do? I multiplied row 1 by a negative 2 to make those exact opposites, and I added those. So if I was to look back, if I look at the numbers, if I want to get rid of the x here, well, isn't that the same idea? Don't you multiply this by negative 2? And just add those? Well, guess what? That's what this says. This says here. Take row 1. Remember, this is row 1, this is row 2, in case you've forgotten. Equation 1 is defined by row 1, equation 2, row 2, and column 1, C1, column 2, C2, and so on and so forth. So, if I look at this, this says multiply, take row 1, multiply it by a negative 2. If I multiply this by a negative 2, what would happen? I will get negative 2 times 1, a negative 2, a 6, and a 6. And do you notice they didn't do anything to row 2, they just said write it down and add those. If you add those, what do you get without the matrices? If you add those, wouldn't you get a 0, 1, and a 2? Except, what do they say? They say put that in row 2. So what they're saying, hey, they're saying (1, -3, -3). They're saying, even though you may be using row 2 and making calculations, we want the result of this to be put right there. And if I know that this is x, this is y, and this is z, hey, can't I say y equal a 2 just like we got y to equal, wait, a 2 or a negative 2? Oh, that was a positive 2. Look, you guys made another mistake. You gotta be careful. Right? So that's the idea. Now, you're not solving here. You're just following what they're doing. We're getting used to this. I'll tell you the big secret. The big secret is when you start a matrix to always make that a 0. We're going to follow certain process of solving matrices, and it turns out to be a lot more efficient than systems of equations. So if I pick another problem, if I look at number 24, and this is a 3 by 3, they're asking me to perform 2 operations. Well, let me see if I could do them. Of course I can. I'm just, oh boy. So, this is a matrix. They would like me to perform the following operations. Row 2. When they say put in row 2, they're talking about this row. They say, and notice what we want. We would like this to become a 0, and we would like for this to become a 0. That's always what we do. we always want in our first step to take the very first entry, whatever that is, and make everything underneath it a 0. To do that, well, think with me. If I multiply this by 6 and make it a negative, and notice what they said to do. Multiply row 1 by negative 6, and if you add it to this row, add it to row 2, but put the result in row 2. Well, let's see. If I multiply row 1 by a negative 6, wouldn't that be a negative 6, an 18, a 24, and a 36? If I copy row 2 down, wouldn't that be a 0? This would be a 13. This would be a 30. And this would be a 30 as well. There it is, done. If I take row 3, and look at these. Do you see if I take row 1 and add it to row 3, that will do it? And there it is. Take row 1, take row 3, and add those. Now you notice they didn't say anything. They didn't say anything about row 1, which means you really do not use nor change, you just copy it down. So every step of the matrix, you're going to write everything out. That's always the case. And that's it. That's all they want. Now I do want to point one thing out. If this is x, this is y, this is z, look at the last row. Do you see that I could tell that negative 2y equal 0? That's not needed for this problem, but just saying. For now, we're just applying those properties, and that's all we're going to do. It's not that challenging, just different, nothing more.
Alright. Next set of problems says, solve each system of equations using matrices or row operations. If the system has no solution, say it is inconsistent. You could just say no solution. That's not a problem. So this is how we're going to use matrices. For now, we're going to use augmented. Our goal is always to make that a 0. How do we do that? In this case, it's easy. Take row 1, multiply it by a negative 1, and add it to row 2. And we want the result to stay in row 2. So let's see how this works. If I multiply row 1 by a negative 1, doesn't this become a negative 1, a negative 2, and a negative 5? And if I add those, wouldn't that be a 0, a negative 1, and what is that, a negative 2? I'm going to take row 1 and just copy it down. And pretty much that's as far as we're going to get. Why is that? Because look, if this is x and this is y, if I go back to the equation, doesn't that say negative y equal negative 2? Actually, doesn't that say negative y equal negative 2? Which means y equals a 2. And this is called backward substitution. We go a level above, a step above. We say x plus 2y equal 5. But I know what y equals. So if I plug that in, guess what? I got the equation. X plus 4 equal 5. So x equal a 1. The solution to this system of equations is 1, 2. Back in the days, you graph those two lines, you use the substitution method, you use the elimination method. All of these work. For now, we want to start using matrices. And what does that mean? That means if you replace x equal 1 and y equal 2, in the first equation you'll get a 5, in the second equation you'll get a 3. That's what that means. Okay, I'm going to stop here and start the next video, finish this up.